Huh?
Whatever yesterday.
What? What's the question? The quiz? Yeah. No, and there's a video of me going over it on Moodle. Right? So, study. Okay, our first test this Friday, the review materials, if you saw my announcement, went up yesterday. Okay, so you can log into Moodle. How many still haven't logged on to Moodle yet? Okay, so make sure you do that if you plan on studying. If you need any questions, stay after school. Don't Google Dublin Cossman Moodle. It will take you to the wrong thing. Make sure you go to the URL that is on the handout that you're given the first day of school. And if you need any extras of those handouts, I have extras. Okay, x to the fourth minus 6x cubed plus 11x squared minus 10x plus 2. Okay? This is a very good problem, very special. All of the concepts pretty much that we have talked about go into this problem. Okay, so very, very complex. It'll make sense, but it's a pretty complex analysis we're going to do to this. Okay, how many zeros does this polynomial have? 4. Could all 4 be real? Could 3 be real and 1 imaginary? How do you know that? Because all the coefficients are real. Because all the coefficients are real, the imaginaries must come in conjugate pairs. Absolutely, that's great. So there could be 4 reals, 2 reals, 2 imaginaries, or all 4 imaginaries, right? Sweet. If I am to find all 4 zeros by hand, then I am going to keep my fingers crossed and hope that at least 2 of these zeros aren't just real, but are actually what? Rational. And if they are, what numbers could they possibly be? 2, 1, -2 and -1, but if you look even more closely at this polynomial, look at the number of sign changes. How many sign changes do you see right now? 4, so that could be 4, 2, or no, positive real zeros. But look at the negative real zeros. How many sign changes do you see? None. So there aren't any negative real zeros. So therefore, the only possible rational zeros are 1 and 2. That's it. So let's test them. We start with 1. So we've got 1, -5. What is this? 6, -4, and not 0. Let's try 2. 2 and -6 is -4. 3, -4, -6. Uh-oh. Okay? So none of the zeros we now know are rational. So either all 4 are irrational, 2 are irrational, 2 are imaginary, or all 4 are imaginary. But do I now have any hopes of finding all 4 zeros completely by hand? No. Not unless, you can make just this crazy guess. But what we're going to do is we're going to use our calculator, but we're going to make it look like we made the crazy guess. I should be able to take your papers, hand them to another math teacher, and they're going to be like, what in the world? This student just found all 4 of these zeros by hand, and none of them are rational. This kid's a genius. All right, where did they come up with this? It's incredible. Okay, so let's graph this thing. Let's get the handy-dandy graphic. Oh, there it is. That was quick. Okay, so that is the graph of x to the 4th minus 6x cubed plus 11x squared minus 10x plus 2. So now that we see this picture, and I'll give you time to go ahead and type that in because you are going to want to follow along. Well, I now know that 2 of the zeros of this polynomial are what? Even more specific than real. They have to be irrational. I know they can't be rational because my only hopes at rationals were 1 and 2, and this clearly is not 1 or 2. So those have to be 2 irrational zeros, and so therefore the other 2 zeros are what? Imaginary. Okay? So we've got two irrational zeros and two imaginary zeros. Well, because all of the coefficients were real, I know that the two imaginaries must be what? Conjugates of each other. And because of that, they both come from a single what type of factor? Quadratic. Okay? So I know these two, the imaginary zeros, come from a single quadratic factor. Okay? So by process of elimination, what type of factor must these two irrationals come from? Also has to be a quadratic, because what is the degree of this polynomial to begin with? Well, that tells me something about these two irrationals. The fact that they both come from a single quadratic factor, and I know that because of the process of elimination, what can you then tell me is true about these two irrational zeros? They are also conjugates of each other. Okay? They have to be. That's nice.
You know that the two irrational are quadratic.
Because the imaginaries have to be. This is a degree 4. So if it's a degree 4, and one of the zeros, and one of the factors is a quadratic, then that means, what do you multiply quadratic by to get a degree 4? Another quadratic. Okay? And the fact is, because all these coefficients are nice, then quadratic factors are going to have nice coefficients, and whenever you have a quadratic factor with nice coefficients, the irrationals are conjugates. Okay? So we're going to use that to our advantage, the fact that we know this now. We know that not only are there two irrational zeros, I know they are going to be conjugates of each other. Okay? So let's go back to our graph, and let's actually have our graph find what these zeros are, but the thing is, your calculator isn't perfect like we are. It cannot tell you what the irrationals are in radical fractional form, can it? What's the only form with which your calculator can present these irrational zeros? Decimals. Okay? Well, we are going to eventually find all four of these zeros in perfect, exact, radical, and fractional form. But we first have to have the calculator give us its estimate, its decimals. All right, so we want to go second and then go to the calc menu. Is everybody familiar with this menu? Okay, you should, everybody should have familiarity from Algebra 2 with zeros, minimum, maximum, and intersect. Which one of those do we want to use right now? Zeros. We select number 2. It asks you 3 questions. It asks you for a left bound, a right bound, and a guess. These are all x coordinates you're going to be entering in. So let's take this 0 right here. It looks like it's really close to 0, but it's just to the right of 0, maybe 0.1 or something. I need to enter a number that's close to that, but is clearly to the left of it. What would be a good choice? I think I feel pretty confident 0 would be a good choice. Maybe to play it even more safe, I might enter -1 and then hit enter. Now it asks you for a right bound. What is a number that is close to that 0 but is clearly to its right? How about 1? And then it asks you for a guess. In most cases, you have to give it a guess that's between your left bound and right bound. Like I couldn't give it a guess at 2. But you can usually give it the worst guess in the world. I usually just hit enter right away. So I end up guessing the same thing I entered as my right bound. And there it is. 0.2679419. I know for sure that's an irrational number. You cannot express that as a fraction. It's a decimal that goes on forever and ever and ever. Never has any repeating pattern to it. Make sense? Does everybody still have the word 0 written on the screen? That's the key. Before you ever start writing down numbers from your calculator, make sure that word 0 is still there. Because if you accidentally bump your cursor, whoop, a lot of people, well, that looks the same. What? There we go. Like that. A lot of people like, that cursor sure looks like it's blinking on that x-intercept, right? You see y equals 0, but that cursor's not even on the graph. Okay, you can move this cursor all over the place. That's not on the graph at all. It's not tracing. So if you accidentally hit an arrow key after you find a 0, you're going to end up copying down the number that's not the 0. Okay? So we go second calc 0. Let me find that again. So maybe 0, 1. Okay. With that word 0 there, click to the home screen. Everybody find the X button on the calculator. Press it and then hit enter. What? That number looks familiar. Right? Press the Y. Alpha, Y, hit enter. 0. Look at that. Your calculator is actually constantly storing into the X variable and Y variable of your calculator the current location of the cursor on your graphing screen. If I go to graph and I start moving this guy around, if I quit back to the home screen and I say what is X and what is Y, it's going to give me the X and Y coordinate of where that cursor is. Pretty cool, right? So, I keep messing mine up. Let me find this again. 0, 1, enter, enter. Nice. Here's my 0, quit. I want to actually store this for later. The problem is when I go to find that next 0, what's going to happen to this number? It's going to get replaced. So I want to store that into any other variable. I'm going to pick the letter A. So I say, hey, X, I want to store you. So find the store button right above the on button. And I'm going to store you into the variable A. Okay? And you don't have to worry, like, if you have any computer programming experience, a lot of times, like, you're not actually storing a new value in, you're just storing a pointer to that old one, so that when the value changes, they all change. It's not the case. X can change and A won't change. A will have that decimal value stored in there, even if X changes. So I've now got 0.267949192.4 and a few more decimals after that stored in for A. Okay? So if you look, there it is. I can say, hey, what's 2A plus 3? I don't know why we would do that, but syntax error. Grab my 3. There we go. Hey, there's 2A plus 3. You can do all kinds of cool stuff, right? So now let's go back to our graph and let's find the second 0. Second calc 0. What's a good left bound? 3 looks good. About 5 for a right bound. Give it a guess. Boom, there it is. What happened here? Look at that Y coordinate. -7, -12. What is that? You ever wonder how your calculator is finding zeros? Do you know how it's finding them? Guessing and checking. It's plugging a number in, and it's seeing how close the output is to 0. And there's a tolerance. Because will it ever find the exact number that makes it output 0 exactly? No, it can't, because your calculator does not store all infinity of the decimal places of these numbers. That's impossible. If Texas Instruments could create a calculator that could store all infinity of these decimal places, they wouldn't be making graphing calculators, because they would have a infinite gigabyte hard drive. Probably better uses for it than a graphing calculator. They can't. They only store like maybe 14 decimal places or something like that. So what they do is they just keep plugging a number in, and if it's close, they get even closer. So they're slowly honing in on this decimal that makes the output not 0 exactly, but close enough. And apparently 12 decimal places is what the calculator considers close enough. Okay? So that's actually 0.0000000000007. That's 0. We can treat that as 0. You see that a lot in these calculators. Okay? So let's quit to the home screen. Let's take that number and let's store it in for B. Okay? So now I've got one of the zeros entered in for A. I've got the other 0 entered in for B. 0.267949192.4, 3.732050808. Cool? Okay. Well, that's nice. Those are not exact answers. Those are good estimates. They're accurate to like 12 decimal places, but that's not good enough. So what can we do with these? Well, I know that these two irrational zeros come from a single quadratic, and I'm pretty sure that the coefficients in this quadratic will be very nice, right? Rational even. So let's create linear factors Remember, A is one of my nasty decimals, B is the other nasty decimal. And let's FOIL this out to actually create the quadratic that they come from. So we've got x squared minus bx minus ax, and then this becomes a plus ab. Except I really want these middle two terms to be combined like terms, so I'm going to factor a negative x out. And so I get something like this. So apparently, if I take those two decimals and add them together, and then take the opposite of that number, I should be able to get the middle coefficient of the quadratic that they came from. If I take those nasty decimals and multiply them together, I should get the constant term for the quadratic that they came from. And I am pretty sure that those two numbers are actually going to be nice, not nasty irrational decimals. So let's go back to our calculator. What do I get when I add A plus B together? Holy cow! It's just 4. Those are nasty decimals. Add them together, you get 4. What do I get when I multiply A and B together? Holy jeez. 1. How about that? So what is the actual quadratic that those two nasty irrationals came from? X squared minus 4x plus 1. Pretty sweet, huh? Isn't that cool? Okay, so let's disguise some of this work because I want to make it look like I just guessed that. Okay. So here's how this works. So we've got this polynomial. It's a degree 4 polynomial, right? We've got this degree 4 polynomial. I tried all of the possible rational zeros, and none of them worked. And so now we go, oh, poo. No rational zeros. Whatever am I going to do? Well, luckily, I know x squared minus 4x plus 1 is a factor. And so now people are going to be like, what? Where did you get that? And you just say, it doesn't matter. You don't worry about where that came from. Let me just at least prove to you that it actually is a factor. Right? Because people are like, you just made that up. There's no way that's going to be a factor. How many possible factors are there for you to guess from? There's infinitely many. There's no way you're going to just create one and say, yeah, that's going to work. But then when you actually start doing the division and it works, it's like, oh, genius. Incredible. Here's the thing. Are our calculators perfect? No. When you add those numbers together, is there a chance you weren't actually supposed to get 4 exactly? You're supposed to get 4.000003. But your calculator has so much rounding error that it just says, oh yeah, this is 4. Okay? So there's a chance when I actually go to test whether or not this is a factor or not, it actually tells me it's not. But if it works, if I divide this out and I get a remainder of 0 exactly, then we just found one of the quadratic factors. We just produced out of thin air an actual quadratic factor. Now the reality is we use our calculator, but even still, that calculator technique, it's not necessarily foolproof, but it at least gives you something to try, right? So how can I truly determine whether or not this is a factor of that polynomial or not? Divide it out. And because it's a quadratic, I cannot use synthetic division. We have to use long division. Of which I know a lot of you have been disappointed. We've been using synthetic a lot lately. You find long division to be very fun. So you're welcome. Because the only rational zeros that could possibly work are 1 and 2, and I tried them, and neither of them gave me 0. Okay, so let's divide this out. Hopefully I get a remainder of what? If I do, we did it. We just pulled off the impossible. We produced, we guessed, using our calculator and some very inaccurate decimal approximations, we just created a quadratic factor. So let's long divide this thing out. What do you multiply x squared by to get x to the 4th? So that gives me x to the 4th minus 4x cubed plus x squared Subtract, that's 0, that's a minus 2x cubed, and that is a plus 10x squared. Drop down the minus 10x, and repeat. What do you multiply x squared by to get negative 2x cubed? Negative 2x, so that gives me negative 2x cubed plus 8x squared minus 2x. We subtract down again, that's 2x squared minus 8x plus 2. What do you multiply x squared by to get 2x squared? 2. So we have 2x squared minus 8x plus 2. When we subtract, what do we get? 0. Boom! Did it.
I did that without all that. All you have to do is make it the two factors like you're doing in quadratic, or not, yeah, but whatever, instead of 4.
Oh.
Like, so instead of x, it's x squared.
Yeah, we'll actually see a problem later where we actually use that technique. I still think that's kind of hard for quadratics.
I thought it would be.
So here's what... So we had one of the factors, x squared minus 4x plus 1, and you know that it's going to be some quadratic that we're multiplying it by. But because the leading coefficient is 1, what does the leading coefficient of this unknown quadratic have to be? It has to be 1, x squared, right? Because the constant of this is 2, and we see a 1 here, what does the constant of this quadratic have to be? But then how did you find the middle one?
Negative 4. I think you have to add for the, you would distribute the x squared to the other one, so it had to be negative 2, so you add negative 4 and negative 2, you get negative 6. And then the middle term is just 1.
So let's go ahead and call this something x. So you're focusing on the x cubed term. Negative 4x times x squared gives you an x cubed term, but so do these two.
Exactly.
So negative 4 plus what gives me negative 6? And so that's how you got negative 2? Yeah, that's cool.
Will that work every time, or
that would work every time. It's a lot easier as well if your unknown factor is a linear. If your unknown factor is a linear, that is way better than using division. If your unknown factor is a quadratic, you can see figuring out that middle term was a little bit not as easy. If it's a cubic or degree 4, just do long division, right? But no, I like that. That was good. We actually use that same exact technique in another problem we're going to do at the end of the lesson today. That was good. Nonsense. It's called long division nonsense. You're nonsense. All right. So here's what we found. Nene.
How will you do long division
You have to fill in that term with a 0. So like, there was one in the homework, I think it was like x squared plus 9, there was no middle term, you have to put 0x in there. And every term missing here, you need to fill in the 0x as well. Does that make sense? Good. All right, so here's what we have. I now have the 2 quadratic factors of this degree 4 polynomial. I know that x squared minus 4x plus 1 is the quadratic factor that gives me my what zeros? Irrational zeros. And then this quadratic factor, x squared minus 2x plus 2, is the factor that gives me my imaginary zeros. That's great. So how do I actually find those zeros from these? Quadratic formula, right? So let's start with this one. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What is the square root of 12? And that can be simplified because everything can be divided by a 2. So you get 2 plus or minus radical 3. Those are your irrational zeros. Let's verify in my calculator if I say, hey, what is 2 plus the square root of 3, calculator? If I compare that to what I have stored in for b, hey, they're exactly the same. And if I say, hey, what is 2 minus square root 3, calculator? Compare that to what I have stored in for a. Well, what do you know? They're the same. I want to try something. I want to ask my calculator to test if A is in fact equal to 2 minus radical 3. Okay, if you remember, what will my calculator output if this is a true statement? A 1. If it's false, it'll output a 0. What do you predict? I predict it'll say false, though I would not be surprised if it still says true. You never know what's going on in all these decimals, right? A was found by the graph estimating where it crosses the x-axis. That might only be accurate to 12 decimal places, and it might find the square root to be more accurate. I don't know. Let's find out. It said true. So it actually estimated them to the same number of decimal places accuracy, and that worked out. I'm a little bit surprised. We know that they should be equal, but I'm surprised. I would not be surprised if my calculator actually told me that they were not. Here, I want to check this one too, because this is the one that didn't show a 0 for the y coordinate, was it? So it sees them as being equal. Very cool. I could definitely see a situation where even though they are the same, the calculator doesn't think they are because of that rounding accuracy. Okay, let's find the two imaginaries. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. What is the square root of negative 4? 2i. Well, everything there can be divided by 2. So we get 1 plus or minus 1i. So our zeros are 2 plus radical 3, 2 minus radical 3, 1 plus I, 1 minus I. In exact form. Okay, something our calculator could not do. Our calculator could give us decimals for all of these, but not exact. And the beauty of all of this, if you were to take all this work, print it out, and hand it to a math teacher, they would think you actually found all 4 zeros completely by hand. There would be this step here where I say, but I know x squared minus 4x plus 1 is a factor. And they'll be like, how do you know that? And then you divide it out and get a remainder 0, and then they're like, oh, well, they're right. I don't know how they found it, but they're right. Right? And sometimes that's how math works. Sometimes things are these intuitive leaps, but as long as you prove it, you can't question it. Einstein was supposedly, he always had these intuitive leaps where he would jump straight to like this conclusion that was correct, but he couldn't explain himself. Like, we could explain ourselves, we cheated. But he actually just would jump straight to these brilliant ideas and had no explanation for how he got there. He just understood it. Yeah, we'll be going to some more stuff. Cool. So wasn't that pretty neat? I like that problem. I think it's pretty cool. Using a combination of, we couldn't have done this without our calculator, but our calculator couldn't have done it without us, right? Your calculator couldn't have gotten that exact. No way. But we couldn't have gotten that without our calculator. It's this perfect combination of using the tool but still using your brain. What if I were to ask you, factor this polynomial completely over the set of complex numbers? Factor this degree 4 polynomial completely over the set of complex numbers. What would you write? How many factors would you be writing down? You'd be writing down 4, and they would all be what? Linear. Whenever you're factoring over the set of complex, you literally have one linear factor for each of the zeros, no matter if they are rational, irrational, or imaginary. So that would be x minus 2 minus radical 3, x minus 2 plus radical 3, x minus 1 minus I, and x minus 1 plus I. Agreed? Now, what if, however, you are asked to write the factors of this polynomial when factoring over the set of only real numbers? Then you would have how many factors written down? 3. Which of these 4 factors here are still okay when factoring over the set of reals? the two irrationals. Those are real numbers. Those are great. It's these two here that I would have to FOIL together and write as x squared, what was it, minus 2x plus 2? Is that what it was? Well, actually, I can easily figure that out. What do you get when you add these two numbers together? 2, so there's your minus 2. What do you get when you multiply these together? 2, so there's your plus 2. That little trick. Add them together, take the opposite, that's your middle coefficient. Multiply them together, that's your constant. Has anybody ever taught you that trick? There's actually a name for it. It's called sum and product of roots. We used to teach it, now it's for 2. What's that? If you ever want to FOIL together two factors that are conjugates of each other. If you ever want to FOIL together two linear factors that are conjugates of each other, add them together. So when you add these imaginary numbers together, the imaginary parts cancel, you end up with 2. Take the opposite of that, negative 2, that's going to be your middle coefficient. Then multiply them together. So you're going to get 1 minus I squared, that becomes 1 plus 1, which is 2, and that's your constant. So, just to give you a quick, let's say, what quadratic has, give me an imaginary number, any. What was that? 3 minus 6i. So what's its conjugate? 3 plus 6i. Watch this. X squared minus 6x plus 45. Boom! Pretty fast, huh? Because when you add these together, what do you get? 6, so there's your negative 6. When you multiply them together, 9 plus 36, 45. So, cool little trick, huh? It works with radicals, too. Give me an irrational 0. Give me a number in front. How about 3 plus radical 5? So then its conjugate would be 3 minus radical 5. That's going to be x squared minus 6x plus 14. 9 plus 5. Or, worst case scenario, just FOIL it out the long way like you always did. Yeah. Yeah, if you know that shortcut, feel free to use it. Negative I, it's 1 plus I and 1 minus I.
Like when you see the adding of the two.
Yeah. When you add them together, you just combine terms. 1 plus 1 is 2, but the i's cancel. That's how you get the middle one. Don't worry about the shortcut. If you don't have it, don't worry about it. You can Google it, sum and product of roots.
What's it called?
Sum and product of roots. Now, what if I ask you to factor this again, but over the set of rationals this time? It's going to be 2 quadratics, and those are going to be x squared. What do you get when you add these two together? 4 minus 4x. What do you get when you multiply them? 4 plus 3, 7? No. It's 4 minus 3, 1. Oh, I think I was wrong on this one. It's not 14. It ends up being 9 minus 5 is 4. Oh, geez. That's bad. Okay. So it's 3 different factorizations for this one, depending on what you're factoring over, what set of numbers you're talking about. Rationals don't include imaginaries or irrationals. Nothing but nice numbers, whole numbers and fractions. I FOILed these two together.
Oh, okay.
Now, something I like to do on tests and quizzes is taking this concept, this idea, but asking the question backwards. So, let's suppose, and I would have this all typed down in the quiz. Let's suppose P of X is some function, and I'm telling you that after completely factoring it completely over the set of real numbers, I end up with 1 linear factor and 1 quadratic. Now, I'll tell you what, we'll say this is after being completely, is how you spell completely? Doesn't look right. You ever have one of those moments where you write something, you're like, is that really how you spell it? Yes? Continue. Continuous. I kind of sing it to the tune of Fergie's Glamorous. Continious. I don't know if I remember it. Continuous. It's a math concept. Continuous. So let's suppose I tell you, wow, I cannot spell. Is that how you spell rational? So let's suppose this polynomial is factored completely over the set of rational numbers. What can you tell me about this polynomial? It's got a linear factor and a quadratic factor. It's a degree what? So it has how many zeros? What types of numbers could those zeros be? Could all three be real? Yes, if all three are real, specifically one of them is rational and the other two, and those irrationals would be conjugates of each other. But could it be one real, one imaginary? It could be. It could be one rational and two imaginary. So, when completely factored over the rationals, you end up with a linear and a quadratic. Could be one rational, two irrational, hence all three are real. Or it could be one rational, two imaginary. What if this is not factored over the rationals? What if I say you end up with a linear and a quadratic when completely factored over just the reals? Then what can you tell me? Could all three be real? No. If you're factoring a polynomial over the reals, then all real zeros will be linear factors. So no matter what, this graph has two whats? Imaginary zeros. This linear factor is real. Is it rational or irrational? Could be either. So this could be one rational and two imaginary. It could be one irrational and two imaginary. If you're factoring over the reals, an irrational number is real. So it would have a same linear factor. But imaginaries would not. Then what if I tell you when factoring a polynomial completely over the set of complex numbers, I end up with a linear and a quadratic? What would you say to me? You'd say, Dremel, you're crazy. You cannot have a quadratic factor when factoring over the complex. Everything factors down to nothing but linear. So that would just be simple. Okay? Yeah, that's all I got.